Alrighty. Oh, that's not what I need. This is what I need. Here we go. So, we kind of already talked about this, going through the homework and stuff like that, but you might as well talk about it one more time. Alright, so yesterday, right, we talked about applying calculus with our parametric equations. Alright, because we talked about just doing parametric equations. That was more of a pre-calc review, so we got to make sure we get in the calculus itself here, right? We found that the derivative, the normal kind of like the normal first derivative that we talk about, right, in rectangular coordinates, dy dx, we could rewrite that in terms of t by multiplying the top and bottom here by like a 1 over dt, so we get dy dt over dx dt. So the equation for the, tangent slope to our curve is just merely taking the derivative of the y component with respect to t, dividing by the x component with respect to t. Y times t over x times t. Okay? Super simple. All right? There's no need to eliminate the parameter and then take the derivative. We can just use our two parameters or our two parametric, components there and then just divide them. All right? We talked about how to find horizontal and vertical tangents just by applying, the fact that for a normal horizontal tangent, you want your slope to be equal to 0. So this would only equal 0 if the numerator is 0, right? But then simultaneously to that, we don't want the denominator equal to 0 because then it would be indeterminate form. Same thing with vertical tangent, right? We would want our denominator to be 0, so we would be undefined there. So we'd set dx dt equal to 0, but of course we also don't want simultaneously to that dy dt to equal to 0 because, again, it would be indeterminate form. All right? We did some problems finding the slope of a tangent line, okay, or finding the equation of a tangent line, finding horizontal and vertical tangent locations, okay. Again, be careful here. When it says find points, that means you need to be getting x and y coordinates, not times, right? X and y coordinates. You use the t to get the x and y's, but eventually you need to give x and y coordinates, right? Points. Equation of a tangent line, right? That's just, again, use your derivative at that point, and then there's your point, and boom, equation of the tangent line right there. Okay? Of course, we can't talk about the first derivative without going into the second derivative there. And so with some kind of like manipulation here, right? Okay, just starting again with the idea that our second derivative is the derivative with respect to x of the first derivative. Okay? But again, using that kind of rewriting in terms of dt, we get d dt over dx dt, and then bringing that dy dx up into the numerator there, we get d dt dy dx, which is just the derivative with respect to t of the first derivative over dx dt. Okay? Typically, right, we are going to have a quotient rule here unless you can simplify that first derivative. So again, try and simplify that first derivative to make sure that you can, more easily take the second derivative there. And again, don't forget to divide that by dx dt. Okay, that part too. Okay, we did some problems here, worked through that. Okay, did some more stuff here, talking about some interesting ideas about if the curve is getting closer or further away from the x-axis and y-axis. Okay, so kind of, some new ideas that we were able to do thanks to being able to break apart our x and y components there. And then finally talked about arc length, right? And this was like the very last thing I didn't quite get in all I wanted to do. We compared arc length in rectangular coordinates, which was dx dx squared plus dy dx squared, square root of that quantity, okay? And then integrate from a to b, right? The dx dx symbolizes just 1, so we don't typically write dx dx, we just write the 1 there. But then here, right, for parametric, it's just a slight change. We have dx dt, because now we're taking the derivative of x with respect to t and the derivative of y with respect to t. So those squared, add them up, square root, and you get the interval from a to b there. So it's still using that Pythagorean theorem, okay, idea, side squared plus side squared and square root of that to get the arc length. Adding up all those kind of things. All right. So any questions up to that point? All right, we're back on track to where we were. So then yesterday, right, we got to this point. Okay, we wanted to find the length of the curve whose parametric equation is x equal to cosine cubed of t, y equals sine cubed of t. All right? Excuse me. And so, we need to take our derivatives here, right? We need to take our derivatives. So dx dt, well, we have x equals cosine cubed t, so dx dt, by the chain rule here, right, we're going to have to do 3 cosine squared of t times the derivative of cosine of t, negative sine of t. Okay? Likewise, we also need to find dy dt. All right? dy dt is 3 sine squared of t times the derivative of sine, which is cosine of t. Okay? It's not necessary for you to do this over here on the side. Again, this is notes, so I'm kind of like trying to write it more explicitly here. But if you're confident enough in your ability to take the derivative that you just like, go from this step to then writing, what the integral would be here, feel free to do that. Okay. Our limits of integration, right, will be 0 to pi over 2. Okay. And then square root of, and then we'll, plug in here. So I'm going to make it negative 3 cosine squared t sine t, quantity squared, plus, and then positive 3 sine squared t cosine of t dt. Okay? And so there's our substitution. And of course, if this is a calculator active, like the ones on the homework from last night, right, you can just go ahead and type this in. It's a little messy, right? It's a lot to type in, a lot to keep track of here. But we can actually do this one here without using a graphing calculator. Believe it or not here. So let me just show you what would be involved. Okay, so we'll square these quantities, and so we'll be left with 9 cosine to the 4th of t sine squared of t, right? Plus, and then, oops, I forgot my square there. Squaring this would make a 9 sine to the 4th t cosine squared of t. And there's our dt. Okay. Now, any ideas about what we can do from here?
That's it.
That's it. Done. Not quite. There's a GCF, right? What's our GCF we can factor out here? So we can factor out a 9. And they both have a 9. They both have a cosine squared and a sine squared. So we'll factor out that. So 9 cosine squared theta. Why am I doing thetas now? Cosine squared t sine squared t. Okay. And then what will be left over from that factoring? Well, from this, what will be left over? Cosine squared. And what will be left over from here? Sine squared. Oh my gosh. What's cosine squared plus sine squared?
1.
1. Whoa. Okay, and so we're integrating from 0 to pi over 2 of the square root of 9 cosine squared t sine squared t dt. But, oh my gosh, they're all perfect squares. So it's 3 cosine t sine t dt. Okay, and we can integrate this, all right, using what technique?
That one.
That one.
Oh, you.
Don't need to use integration by parts here. It's just a u substitution. What would we let our u be? Yeah, you can really do sine or cosine here. It doesn't really matter. If you let u be sine, then your du will be cosine, and so you can go from there, right? If you let your u be cosine, then your du would be negative sine. You can take care of that, no problem too. All right, I'm gonna stop there just because I think you get the point from there, right? Hopefully you guys can go from there. Okay, so dot, 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 this would equal 3 halves if you did that, okay? But again, I want to kind of keep moving here. Okay, so just to show you, oops, I guess I should put the dot, dot, dot there. 3 halves, there we go. Okay, so just to show you this is something that we can do, okay, without a graphing calculator. So just keep that in mind, right? Again, it's a little bit funky here with the, the factoring and stuff like that. But anyway, it is possible to use without a graphing calculator. They're not always going to be like awful. Okay, questions on any of that? Okay, so let's take a look then. Let's dive into position, velocity, and acceleration, okay, and how that relates, how we can kind of translate from rectangular concepts to parametric slash, vector form, okay? So we're going to introduce this idea of vectors that we've never talked about before in this class, really, okay? But So let's just read through here, right? So suppose a particle moves along a smooth curve in the plane so that its position at any time t is, and this is purposeful here, this is the notation that you use for vectors, okay? It's like the pointy kind of parentheses here. I don't know what this grouping symbol is called. Mr. Goff said they were chevron, but I don't know if that's the case or not. But anyway, whatever these grouping symbols are called, they're pointy like that, okay? Where x and y are both differentiable functions of t. So essentially all we're doing here, just kind of like make this really simple for ourselves, all right? All we're doing is just kind of like rewriting what we normally see the parametric equations as like two separate things. We're kind of putting them together as a single kind of object, a thing called a vector. And all a vector does, it just kind of like, you know, if you have like a vector like this is important because it has a starting point, right? It has a stopping point right there. All right, it has an x component to it, and that's determined by x of t, right? It has a y component to it, and that's determined by y of t. And then that gives you your kind of like location, right? From here to here is, you know, kind of like where we see that point. All right. All right. So it's not like, you know, anything too crazy there, right? So the vector here would be like x comma y. Okay. So the vector has both kind of like a direction to it, right? But it also has a length to it as well. A magnitude is what you call that, right? And so the magnitude here, which is equal to the length of the vector, okay? Well, how would we find this length? What kind of shape have we created here? It's a right triangle, and so this is the hypotenuse of that right triangle, okay? So the length is just going to be, you know, the square root of x squared plus y squared. Okay. Okay. So that's kind of like, you know, basic information about vectors and stuff like that. But really, again, the idea here, right, we have parametric equations. It has an x part and a y part to it. Vectors have an x part and a y part to it, right? And they change with respect to time here. So these x's and y's will change with respect to time. And it's just a way that we describe position and velocity of the particle and stuff like that, both in terms of the x component and the y component. Okay? So we're told here its position at any time t is xt comma yt. So a particle's position is determined by x of t comma y of t. That's all there is to it. Okay, it's just the, you know, kind of like the x and y component put together there. Okay, kind of like what we've been doing. All right. So we know, right, that position and velocity. How is velocity related to position? What do you have to do? Take the derivative, right? So that's exactly what we're going to do here. The particle's velocity is determined by x prime of t comma y prime of t. Okay, it's just that simple. Okay. Notice what it is not. It is not dy dx. Okay? dy dx is y prime divided by x prime. Okay? So that would be the slope of the curve. But the particle's velocity, we kind of keep the x component and the y component separate here. We find the rate of change of the x component, we find the rate of change of the y component, and so we describe the particle's velocity, we use these two values here. Okay? All right. What about acceleration? How do we find the acceleration given the velocity?
Second derivative.
Right, it's a second derivative. So if x of t is the original function, right, x prime of t is the velocity, then x prime prime of t and y prime prime of t. Okay? So again, this is different from rectangular coordinates when you have like position in y in terms of y and x, you would find d squared y over dx squared, right? Rectangular coordinates is d squared y over dx squared. We're not finding that here. We're just finding x prime prime the second derivative of just x with respect to the second derivative of y with respect to t. Okay. So, particle speed. Well, in rectangular coordinates, I'm going to write this one out here. The speed, what's that related to? The what? Yeah, Sean? Absolute value of velocity, exactly right. I'm on page 2, I think. Okay? The rectangular coordinates are the absolute value of velocity. For our purposes, all right, the speed is going to be the magnitude of our velocity vector. Okay? So there's our velocity right there, right? So that's one leg of the triangle. That's the other leg of the triangle. And so we want to find the hypotenuse of that kind of triangle for the actual magnitude of the vector. So it's going to be square root of x prime of t squared plus y prime of t squared. Okay. So, and again, this hopefully makes some sense here, right? For velocity, when you take the absolute value of something is the distance of that thing from 0, right? Absolute value is not just like this magic function that makes things positive. Why does it make things positive? Because it means distance from 0. So here we're trying to find the velocity, that distance that quantity is from 0, right? So same thing here, we're finding a distance, right? It's the x component squared plus the y component squared. It gives us the distance or the length of that velocity vector. Okay. Notice also, right, does speed in rectangular coordinates, does that indicate a direction? No, it doesn't, right? You take the direction component out of it, right? If I am moving 5 miles per hour forwards or 5 miles per hour backwards, we still describe it as 5 miles per hour with my speed, right? But if I go 5 miles per hour forward velocity-wise, right, so that would be a positive 5 mile per hour distinction, I guess, and then 5 miles per hour backwards for velocity would then be like a negative 5, because again, the idea is there we're going in opposite directions. All right. But the same principle happens here too. We kind of lose the directional component, right? Here, for the velocity, we have a directional component. We can see, we might have a positive x or a negative x. We might have a positive y, x prime or x, positive or negative x prime or positive negative y prime indicating direction. Here, we get a single value for the particle speed, and that would not really indicate a direction. Okay, it would just give you like a quantity, the rate of change there. That's it. Okay, so you would lose it because you're combining all that together in one number. All right. Total distance traveled, right, for rectangular coordinates. Okay, for rectangular coordinates, how do we find total distance traveled?
You take the integral.
Integral of what? The integral of the speed. Which is the absolute value of the velocity. Yeah. All right. So integral of speed, or in other words, the integral from a to b of the absolute value of the velocity. Okay. And the reason why, again, why we make an absolute value there is because we want to, make any sort of if we didn't do absolute value of the velocity, we'd have both positive and negative velocities that would kind of cancel each other out, right? But we don't want that to happen. We want to know the total distance there. So we would make those negative velocities positive so we could add them all up for the total distance traveled, right? Because if you travel one step forward and one step backward, your net change in position, your displacement would be 0, but your total distance traveled would be a positive 2, right? One step forward, one step backward kind of thing. So we want to get rid of that negative 2, that negative 1 step back, and make it positive with the absolute value and stuff. So anyway, well, same idea here, right? If we're integrating speed for rectangular coordinates, we're going to do the same thing for parametric. We're going to integrate speed. So we're going to integrate from a to b the speed, which is square root of x prime of t squared plus y prime of t squared, okay, dt. Does anyone recognize this formula?
Yeah, we just did it.
Yeah, what is it?
Arc length.
It's arc length. Doesn't that make sense? The parametric curve describes the motion, the movement, right, of our object, right? That's one way you can think about a parametric curve. It describes the motion and movement of our object, right? If we find the length of the arc, right, the distance along that curve from A to B, from time A to time B, isn't that finding the distance that you travel along the curve? That's exactly it, right? So that's arc length, all right? So just keep that in mind. Okay, so then particles displacement, all right? So this is just the change in position. Well, we know, so in a basic sense, right, if you know the positions here, all you have to do, you can actually subtract vectors and stuff like that. You can just do x2 minus x1, comma, y2 minus y1. Okay, so you could just subtract their two x positions, subtract their two y positions, and that'll give you the total the displacement. Sorry, the displacement there. Okay, or let's say maybe we have velocity instead. Okay, we can integrate from time A to time B of the velocity. So we'll do dx dt there for the x component of velocity, and then comma, integral from a to b of dy over dt, which is the y component of the velocity. So again, just like how we would find in rectangular coordinates, the net displacement is the net change is the integral of the rate of change, integral of the velocity. We're doing that here, integrating the velocity, right? Dx dt is x prime of t, dy dt is y prime of t. So yeah.
Are parentheses wrong?
Are parentheses wrong? I mean, again, we're describing these things as vectors, and the correct vector description would be with the pointy grouping symbols there. I don't know what their names are, but whatever they are. Okay, I don't know if it is chevron or not. I'll have to look that up. All right, so so we do want to use those symbols. I think it's on purpose that we use those, but I can check on that too, Mario, just to make sure. Maybe it is okay. Okay, I don't know. You physics folks, when you guys do physics and vectors and stuff like that, would you guys all use parentheses or?
Yeah, we just did.
Oh, just parentheses?
Yeah.
What's that? Oh, okay. I got you.
We did.
Like a coordinate, you never use coordinates for your vectors and stuff like that. You use I and j though, right?
Yeah.
Okay, I, j, k, and stuff like that. Right. So this is the I and the j part. But so you never really then put those I and j's into groups.
No.
It's usually an equation.
Right, like a this thingamajigger. No, you're talking about something else. Okay.
Just like the parentheses that,
Uh-huh.
like the sharp ones that turn it off.
Oh, okay, like a little hat.
Yeah.
Okay, gotcha. Okay, very good. Well, I think then, yeah, this is just an alternative way, I think, of writing those same kind of vector ideas. Because you could use the I, the j, well, not the k here, we're not doing 3 dimensions, but you get the idea. Anywho, all right, so there's that. But we don't really, you generally don't see i's and j's and stuff like that in Calc 2. They just tend to use this format right here, for whatever reason. Okay, but it can show up. So anyway, the particle's at rest when, all right, well, in rectangular coordinates, what does that mean if the particle's at rest? Right, the particle's not moving, but what's going to relate that back to position, velocity, acceleration? What's going to be true about one of those things if your particle is at rest? Velocity is 0, exactly right. So in rectangular, okay, that means velocity is equal to 0, right? So for our purposes, okay, our velocity here is x prime of t, y prime of t, right? There's our velocity. So then what do we want to be equal to 0 here? Both. Very good, right? Because if I just say dx dt is equal to 0, well, that only means I'm not moving left or right, but we could still be moving up or down, right? And so we want both dx dt and dy dt to equal 0 here, simultaneously. Otherwise, your particle is not at rest. Okay? You need both the horizontal and vertical component there to be 0. Okay? So, it's a lot of concepts we just threw at you, but the thing is, we already knew these concepts in a different format, in rectangular, and so it's just a matter of translating them into parametric. So that's a lot, though. So questions on any of that we just talked about? Okay, questions on any of that? I mean, again, if you get the idea the position is x of t, y of t, then the velocity acceleration should follow pretty easily from that. Total distance distance traveled, right, is just the arc length. The total distance traveled is just arc length there. That hopefully also is, a pretty quick pickup there. Speed, I can see that being a little bit tricky, but again, imagine it's just the length of the vector there, okay? And then displacement, it is just the change in the position, okay? Or integrate the velocity from A to B there, right, kind of thing. It's the same idea that would give you the net change in the position. And then finally, at rest, hopefully that makes some sense there too. So, all right. If there are no questions, let's jump into a problem here. And you'll want your graphing calculators out for this because it's going to have some stuff we're typing in. All right. So, wow, Mr. Wid told us that on tomorrow's quiz, there's going to be 6 fill-in questions, 6 kind of student-produced response questions, and there's going to be 1 free response question. And here is a free response style question. Interesting.
He's going to be on the quiz.
Ah, what? I didn't say that.
Just guessing. Good one, Mike.
I didn't say that, Mike. Okay. But there's a very good chance, right? Because, again, we haven't talked about any free response questions, really, but here's one right here, and we're going to see them on the quiz. And I did say that position velocity acceleration will be on the quiz tomorrow, so there's a very good chance you'll need to know this stuff, right?
I bet a whole dollar that it's not gonna be like this at all in the test.
I know, right? I will feel really bad if that's the case. I haven't looked at the quiz. I'll look at the quiz, though, and we'll see. Okay, so anyway, let's take a look here at this. All right, at time t greater than or equal to 0, the position of a particle moving along a curve in the xy plane is x of t, y of t. Okay, where dx dt is equal to t minus 5 cosine t, dy dt is 6 cosine 1 plus sine t. That's all inside the cosine there. Okay, and again, notice here we're not given the x and y, we're given dx dt, dy dt, so we're given like the rate of change of those things. At time t equals 3, the particle is at position -1, 2. Okay. So we're given the coordinate there at time t equals 3. All right. Letter A, write an equation for the line tangent to the path of the particle at time t equals 3. So line tangent to the path, that is tangent to the curve, all right? And so if we want to find the equation of a tangent line, what do we need to do? We need what? We need a rate of change, which is the slope, right, of the line, and we need a point. Okay, do we have any of those pieces of information, slope or a point? We do have a point. What is the point at time t equals 3? -1, 2, exactly right. Okay, we don't need to integrate here or anything like that to get our original x and y, functions. We already know that at time t equals 3, we have that point. So we have the point. -1, 2, and that's just given to us there. Okay, why am I writing b? We're not done yet. Okay, now the slope. Okay, we want the rate of change of our curve. Is that dx dt? It is dy dx, right? The curve is described as the derivative of the curve, the rate of change of the curve is combining together those two parameters to make, dy dx there, okay? So we have to remember how to take the derivative of, or we have to remember how to evaluate dy dx. In parametric, that is, what's on top? dy dt over dx dt, yeah, or I'm just going to put y prime t over x prime t because it's left to right. Maybe not, but it makes it look not as messy maybe. Okay, so for our purposes, we've got that, right? We've got 6 cosine 1 plus sine of t over t minus 5 cosine t. Okay, I mean, again, this is like, bless you, this is like literally slope here, right? It's the change in y over the change in x. Change in y over change in x. That is like literally what that is. Okay? And we're going to evaluate this, of course, at time t equals 3. Okay, now, you could spend the time plugging this onto your calculator, or we can just take advantage of the fact that arithmetic does not need to be simplified, and just go ahead and write the equation of our line here in point-slope form. Y minus 2 equals 6 cosine of 1 plus sine of 3 over 3 minus 5 cosine of 3 times x plus 1. And just be done with it, right? That's a sufficient final answer there. No need to type that into our calculator. All right, so that's it. There's the equation of the tangent line at time t equals 3. Okay, let's try another one here. Letter B. Find the time t, okay, so we're looking for a time t, when the line tangent to the path of the particle is vertical. Is the direction of motion of, well, let's just stop right there, actually. Let's just stop right there, okay? So, tangent line, right, is vertical. So that means we want what to be what? Okay, the bottom to be 0, right? So we're talking about dy dx here. We want that to be undefined. Dy dx will be undefined when its denominator is equal to 0. So we want x prime of t to equal 0. Okay, well, we'll set x prime of t here. So let me write that out here. Dy over dx equals undefined, right? That's what we're looking for here. And again, this is for notes. This is not something you would need to write out for your actual, work. You could just probably jump to this point here where we then take the dx dt, which is equal to t minus 5 cosine t, and we'll set it equal to 0 here. Okay. And then how can we determine when t minus 5 cosine t is equal to 0?
Mathematica.
Calculators! Okay, we're going to use our calculators for that.
That's cheating.
Is it?
I don't know.
All right. So to figure this out, it's going to be helpful if we are in rectangular, I would say. I don't think we want to graph this in parametric. So I'm switched back to function here. Okay, like so. X minus 5 cosine x. Okay. And do this. Okay, so it looks like we're equal to 0 at a couple of t values here. But there's only one positive t value here. So we're gonna stick to the positive t value, okay, which is this guy right there. So second trace, okay, 0, left of it, right of it, guess it. About 1.30644. Okay, like so. All right, so there's our time. So we've answered the first part of our scenario here, right? Find the time t when the line tangent the path of the particle is vertical. Boom, right there. Is the direction of motion of the particle up or down at that moment? Up. How do you know? Oh, because the graph is increasing there? You can see it on the picture? Okay. Is that enough of a justification for AP Calc though, right? No, not quite. So what else can we look at here? What is determining the motion of the particle? And specifically the up or down motion of the particle? dy dt, right, okay. Remember, right, what determines the motion of something? Its velocity determines the direction of its motion. What is the velocity? It's x prime of t for the x component, y prime of t for the y component. We're looking at the up or down motion here, up or down. That is a change in y. So we're going to take this t value and do what with it? Plug it into dy dt. So we're going to take dy dt evaluated at t equals 1.30644. And we're going to do that using our calculators. Well, Mike, if you want to sit there and do it by hand, you're more than welcome to.
Maybe I will.
We'll get back to you later. And don't worry, there'll be plenty of opportunities for non-calculator computations tomorrow on the quiz.
Thank you.
Yeah, I know, you're missing that. All right, I'm just going to do that many. I don't need to keep going here. Okay, so hopefully we got negative 2.30588. If you got the rest, 3536 there. This is less than 0, so therefore we would expect what kind of motion? Downward motion.
What?
I'm just going to circle this whole thing here like that. Okay. Covers all our bases. All right. Questions on any of that? Okay, let's keep going then, right? Letter C. All right, letter C. Find the y-coordinate of the particle's position at time t equals 0. Find the y-coordinate of the particle's position at time t equals 0. Okay. So we have a couple options here, right? Option 1, we're just trying to find the y-coordinate of the particle's position. We know dy dt, we're trying to find y of t at 0, or really y of 0, okay? So we could integrate this, right? Get the plus c, use our point here that at time t equals 3, the y-coordinate's 2, to get that c value. But the problem is here, do we know how to integrate this kind of thing? Not by hand, right? Okay? So typically when it comes to like trying to find a particle's position given its velocity, we have kind of two paths we take. One is we kind of like generically integrate the velocity to get the position function, find c, and then plug a time in. But we also, but that's not going to work here because we can't really integrate this by hand, right? But the other option is using that idea of net change, right? At time t equals 3, what is the y coordinate of our position? 2. Okay. Then we're going to add to that the net change, which you remember is the integral of our velocity here. I'll write it out. 6 cosine of 1 plus sine of t dt. But what should our limits of integration be? We know we're starting with position 2 at time t equals 3, and we want to find the position at time t equals 0. So we want to integrate from 3 to 0. Okay. We know the position at time 3 is 2. We're going to integrate from 3 back to 0. We're going to integrate the change in the y, dy dt, right? That's what that is right there. And that will then yield our position back at 0. That will yield our position back at 0 there, right? So that's that again, initial condition plus the net change. That will give us our new kind of, placement and stuff like that. So we'll type that into our calculators here. 2 plus math 9, 3 to 0, 6 cosine, 1 plus sine of t, or x in my case. And I get about 3.6335, we'll say. Okay, is our y position. All right. And lastly, find the total distance traveled by the particle for time 0 to time 3. Okay. So, I just want to back up. I just realized now why. Remember, if you remember back at the problem here for letter B, when we set this thing equal to 0, okay, and we had those negative t values, and I kind of just dismissed those, I have a good reason why. Because we're only talking about at time t greater than or equal to 0 there. So that's why we could dismiss those negative t values there. Okay, anyway, back to letter D here. What do we do to find distance, total distance traveled for a particle? What's the formula? Arc length, exactly right. So the distance here is just the integral from 0 to 3 of the arc length. So the square root of, and, all right, I'll just write this thing out here. So dx dt, which is t minus 5 cosine t squared plus 6 cosine 1 plus sine t squared dt. All right. And again, this is calculator faux show. Plus x squared dx. Yep, okay, 13.45306, we'll say. Okay, now, let me just kind of remind you here too, even though the quiz, won't have calculators tomorrow, on the test you will have calculator active, so this, could be a helpful strategy there. When it comes to typing in these very complicated things, okay, into our calculators, and this is especially for you guys that maybe were in Mr. Goff's class, because I don't know if I've covered this since then. You can use your calculator, maybe I have, but I'll just do it again. We're going to be doing these more like complex calculations, so what I find helpful is to take, for example, our function here, x minus 5 cosine x. I put that in y1, and I'll put the 6 cosine 1 plus sine of x in for y2. So I take what's inside the square here and what's inside the square here and put those in y1 and y2. Then when I go to my home screen and if I do math 9, I want to integrate from 0 to 3, I can do the square root. And now instead of having to retype this whole function here, I can go to the vars button, which is right here next to the clear button. We'll go over to y vars for y variables and then function, because we typed those curves into our y equals, so the function, and there's y1. And we can just do y1 squared, okay, plus, and then vars, y bars, function, y2 and squared, and then there's the dx, and you hit enter. Okay, and after some time, we get the same answer there. Okay, so this is an alternate way where you can like really, you know, maybe be in a little bit more control about what you're typing where and stuff like that, and you know, better able to see your parentheses are closed and that kind of stuff too. Okay, questions on any of that? All right, let's move on here. All right, last one here we're going to do. Excuse me. All right, so this is from the 2002 AP Calculus test, number 3, and this is also calculator active. All right, so the figure above shows the path traveled by a roller coaster car over the time interval 0 less than or equal to t less than or equal to 18 seconds. Okay, the position of the car at time t seconds can be modeled parametrically by x of t is this, y of t is that, and where x and y are measured in meters. Okay, so let's just take a second to appreciate this, right? Typically, when you have seen in the past, right, graphs of things, you've seen like height with respect to time, and you're like, oh, that's what the roller coaster looked like. No, that isn't what the roller coaster looked like, right? But here, this is a better kind of representation of what the roller coaster looks like, right? This is like your x position in the air, your y position, you know, kind of like, well, not in the air, this is like along the ground, I guess I'll say, and then your y position up in the air. So this more, you know, closely represents that kind of idea about your, you know, what the roller coaster would look like, okay, kind of thing. So this is actual position here, not like time versus height or something like that. Okay, so it's a little bit, you know, more precise. And then also they give you the derivatives as well, which is very nice of them to do. Okay, so letter A says find the slope of the path, which is this, right, at time t equals 2. So that means we need to find dy dx and then show the computations that lead to your answer. Okay, so letter A here, all right. Dy dx parametrically is what over what? Y prime over x prime. Exactly right. And so it's just going to be 10, whoops, darn it, I keep doing that. 20 minus t sine t plus cosine t minus 1 all over 10 plus 4 cosine t. And we're going to evaluate that at time t equals 2. Okay. Again, we don't need to use our calculator here because this, when you plug in the 2, is going to be all arithmetic. So you could just, you know, plug in the 2 here, get like 18 sine of 2 plus cosine of 2 minus 1 all over 10 plus 4 cosine of 2. Okay? And you can circle that answer and be done with it. So that's straightforward there, pretty much like what we did before. Letter B, find the acceleration vector. What is the acceleration vector again? Okay, you can flip back there if you need to. It's x prime prime, comma, y prime prime. Yeah, that's all there is to it. We just take the derivative, you know, this second derivative. But we already have the first derivative with respect to t, so we'll just take the derivative of these two things. That's all we got to do. Okay? But we're going to find the acceleration vector of the car at the time when the car's horizontal position is x equals 140. So do we actually need to find x prime prime of t? We only need to find x prime prime of 140. Okay, and that's it, right? We don't even need to find y prime prime. We're only finding when the car's horizontal position is x equals 140 here. Okay. So we know that t is 140. Or sorry, t is not 140. X is 140. So me putting in 140 here, that was incorrect. Let me back up here a step real quick. Sorry about that. Okay. Jumped ahead of myself. X is 140. What's t? We don't know what it is, right? But we can find t, right? The car's horizontal position is x equals 140. we need to find what the time value is then, so we can then find the acceleration at that time. Okay, so we're going to use the fact that x is 140 to get a t value, and then at that t value we'll find then the car's acceleration. Find the acceleration vector of the car. My apologies there. Okay, so, sorry, backed up there a little bit. Okay, so we got to find the time when the car's horizontal position is 140, and then use that to find the acceleration vector at that time. So if x is 140, and we want to find the time, what are we going to do with that 140? Set it equal to the 10t plus 4 sine t, the x position there. So 140 equals 10t plus 4 sine of t, right? Set those two things equal. Okay? And then we'll be able to, let's see here, well, I'm going to make this a little bit easier for ourselves. I mean, we could at this point use our graphing calculators and solve this. We could graph 140, we could graph 10t plus 4 sine t, right, and see where they intersect. I'm going to recommend that you subtract the 140 over, like so, because now we're looking just for zeros of this function. I think it's a little bit easier to find zeros than it is to find points of intersection. All right, so let's just find the zeros there. And again, it's not necessary to be in parametric here. We're just trying to find the zeros for a single function, so we'll just go, I'm going to stick to function mode here.
How do you set these ones in the parametric?
Mode button. Yeah, it should be the same direction there. Mode button, and then there's PAR there if you wanted to do that. Okay. But anywho, let me go back to my thing there. 10x plus 4 sine x minus 140. Okay, I graphed it on my typical viewing window there, and it didn't show up, so I'll need to expand my horizons here. Let me go negative 20 to 20 maybe. Aha! So we have a hit there. So we'll find our 0. Okay, so there are my cursors to the left of the 0. There are my cursors to the right. And we'll go in towards the 0 there, hit enter. So at about time 13.647083, and again, I'm going to write that entire time out. I don't want to do the intermediate rounding here. Okay, so we'll say at about t equals 13.647083, like that. Okay, don't round that. That would be considered intermediate rounding. You're going to lose, accuracy with that. Okay, we've got our time. Now we need to find the acceleration vector of the car. That means we do need to find x prime prime and y prime prime at this time value here. Okay? X prime prime and y prime prime at this value. Is it necessary for us to come up with the actual functions, though? We have our graphing calculators. And remember that your graphing calculators can find the value of the derivative at a point for you. Okay? So what we'll do, so we're going to do x prime prime of, that t, and y prime prime of that t as well. Okay? We're going to do that using the derivative command on our calculator. Okay? So I'm going to do math 9 is for integration, math 8 is for the derivative, right? So the derivative with respect to x of, and we'll do the derivative of x prime first there, so 10 plus 4 cosine of x. Oops, I should close that parenthesis, I think. And at x evaluated at that 13.647083. Okay. So I get about a negative 3.529. Comma, and then we'll do the value of the derivative at the y prime component there. So 20 minus t sine t plus cosine t minus 1. Okay, and about 1.2257. And so there's our acceleration vector. You can. You can if you want to. Again, if you don't want to have to worry about it, just give 4 or 5 even if you want to, and the people will just cut off. Your grader will just cut off afterwards. Okay, so again, that was using the derivative there, derivative function. Okay. Letter C, find the time t at which the car is at its maximum height, and find the speed then in meters per second of the car at this time. Okay, so if we're trying to find the car's maximum height, that means we want to maximize our y position, right? Our y component here. We're not really worried about the x component, just the y component. Okay, and so to find those maximums, we want to know when y prime of t is equal to 0. Okay. So we can graph y prime here and see when it equals 0. Okay, graph it. Assume 4 here. Or actually assume 6. Let's do that way. Oops, there we go. So we can see here, right, that our y coordinates, right, are positionally here, we kind of have, you know, a maximum here, and a maximum here. But we can see that those maximum heights are diminishing. Okay, these maximum heights are diminishing. And so we're going to use just the very first place where it equals 0, okay, because that will be where our derivative is 0 there. Okay, so our derivative is going to be 0. The y will be 0 right there. And so we want to find that height, right? And so it's going to be this first t value here. And if we do second calc, 0. Okay, we get about 3.023915.8. Okay, and then the speed, okay, excuse me. The speed at that time, remember speed is, if we go back, it's the square root of dx over dt squared plus dy over dt squared. Okay, and we're going to evaluate that for when t is equal to the 3.023915.8. Okay, now, what is dy dt going to be at this time? It's going to be 0, right? Because how did we find it in the first place? We found this t value when we set the derivative of y equal to 0. So dy dt evaluated at that time is going to be 0. And so we really just have to evaluate dx dt at 3.02, you know, et cetera, et cetera, et cetera, et cetera. Okay, so this is going to equal 0. And so it's just going to be the square root of dx dt squared, which is really, I guess, just the value of dx dt. So anyway, we'll finish simplifying that out here. So 3.023915.8, and we'll then plug that into x prime. So 10 plus 4 cosine of x, or t, I mean. Okay. So if we take the square root of, I don't know, dx over dt squared, and evaluate it at t equals 3.023915.8, we get approximately 6.0276. Okay, and so there's our value there. Okay, the speed. Okay. All right, the last one here. Any questions up to this point? All right, last one here, letter D. Now it says for 0 less than t less than 18, there are 2 times at which the car is at ground level. That's when y equals to 0. Okay, find these 2 times. So we're going to set our position here, y equal to 0. Find these 2 times and write an expression that gives the average speed in meters per second of the car between these two times. Do not evaluate this expression. Okay, so we got to figure out when y is equal to 0. So we'll set, again, that we'll type that into our calculator here. 20 minus, I already had it in there, whoopsies. 1 minus cosine of x. Extend out my so there's the first time it equals 0, and there's the second time it equals 0 there. The question, how do you know when to be parametric or polar? So to know in this case, since we're only trying to worry about when this is equal to 0, we're just worried about the single function there. We're not trying to graph both of these simultaneously. So since we're only in one function, we can just use the function stuff and just treat this as a single function unto itself.
Okay.
That's all. If if you're trying to graph both, you'd want to use the parametric then. That's all. Okay? So sorry, I know I overheard your conversation there, but I want to make sure you answered the question. Okay, so 0 is at 6.28. Approximately 6.2831842. That's time 1. And then time 2, I'll just go ahead and do that. You guys can see on the calculator yourselves if you'd like. And then time 2 is approximately 12.56637. Okay, and then finally we're trying to find the average speed between these two times. Okay. Well, how have we found the average of something in the past? Or the average value of something in the past? What we do? 1 over b minus a, integral from a to b of that thing, right? So if we were trying to find the average speed, we're going to do exactly that. 1 over... I'm going to use T2 minus T1 here because I've already designated those things. I'm not going to write out those numbers again. You should be fine once you designate those in your problem there to reuse them like that. Integral from T1 to T2, okay, of the square root of, so we're going to integrate the speed then, right? Average speed, to find average value of something, it's 1 over b minus a, integral from a to b of that thing. So we're going to integrate the speed. Speed, if you remember, is the square root, right, of, in this case, x prime of t squared plus y prime of t squared, dt. Okay, and there's our setup for the average speed. Wowzers. Okay. Questions on any of that? Okay, Sean, question? No? Can you just keep it as 2 pi and 4 pi? 4 pi? Sure. I don't see why not. Yeah.